Okay, everybody. Let's start again. Welcome back, everybody. I had an interesting chat in the interval. And the one thing that I can promise you about this next section is that the algorithms that you will see are so simple as compared to algorithms you've seen before. So why on earth are you seeing these algorithms? The idea is that we can apply those methods to any problem. So it's a very generic way of looking at problem solving. So I know that probably most of you could program specific solutions to all these problems relatively easily. But the nice thing here is that all we have to do is to translate all these different kind of problems into the state space paradigm and then apply these simple algorithms. And the algorithms will become more complicated tomorrow, and they will be even more complicated on Thursday. And once we have learning, it's even more complicated, but still essentially they are relatively simple. What we try to do is to understand what are the properties of these algorithms and which one to use at which part of the problem solving, which is the appropriate method to solve. And in the end, if you really want to build an intelligent system, you will have to tweak and to program more involved algorithms. But the general idea is one that is applicable to any games. So this is how people solved the chess problem 20 years ago. The basic idea is how people solve the Go problem, and it's all based on these very simple algorithms. So let's look at these algorithms. This is a slightly more formalized version of the pseudocode of the tree search algorithm, and I really want to go into that through this algorithm because it's important to have. So basically, what we now have is a data structure called a fringe in the rest of the lecture, where we order all the nodes that still have to be expanded. So that's our data structure that contains the nodes that we have created in the expansion of one of its parents, and now they are awaiting further expansion. And in this fringe, we put the first node, the initial state, we turn it into a node, and we add it to the fringe. That's all we do. And then we have a loop, a very simple loop. If the fringe is empty, then we don't have any nodes we need to expand anymore, and we're done. And as we haven't found a goal, we report a failure. If it's not empty, then we take the first node out of the fringe, and then we check whether any of the nodes of that we take out of the list, in this case, whether it's a solution. If it's not, then we just expand the node and add it to the fringe. And the point here is that the way we expand this this node determines how we search. And this gives us 4 different search strategies and several more tomorrow. These are the uninformed ones. So we don't know anything about the states, and we just consider them to be blind mathematical objects. Yep.
The fringe is just a list of the leaves?
No, it's a list of, it's not necessarily a list. Let's start with that. It's a data structure that keeps the nodes that still needs to be expanded in memory. And yes, you're right, they are the current leaves, the leaves at the state that you're in. Okay, so the first option that we have is what kind of data structure are we using for storing our nodes that need to be expanded? And the first option is to use a FIFO queue. And most of you, I don't know, probably know what the FIFO stands for. And if you don't know, then just remember our British friends who are so good at queuing. So how does queuing work? The first to come are the first that are served. Yeah. So if you come to the bus stop You stop in front of the bus, and then the other people who come later, they queue behind you, and you are allowed to get in first. So FIFO stands for first in, first out, and the data structure is a queue. Yeah? So how does it work now? It's just exactly the same algorithm we had before, but now we have this data structure which is a queue. So suppose we have this state space for which we want to build the tree where we have an initial node A. And how does the algorithm work? We put A in our queue. Let's say this is our queue, and we put A in it. Yeah, that is step one of the algorithm. Yeah. Breadth first search. And you will see that because we now expand the node, the tree in a breadth first way. So we go into the breadth first, and we see later there will be an algorithm called depth first, which has a different behavior. Yeah? So we start with A, put it in the fringe, and then we go recursively further. This is the only node in the fringe, so we have to expand R. And what are we getting is the two children of A are B and C, and we put them in the fringe. So we put them just in here. And then in the next round, we take out the first one. The first one is B. Yeah?
Is it possible that the fringe contains nodes from different layers?
That depends on the data structure that you use. Yeah, we'll see that in a minute. It will do if you use a different data structure. Yeah? So here we now have expanded B. Have to expand B, so we've chosen B, we deleted it from the fringe, and we now have to expand it. And we do that by adding the children of B, which are D and F, and because it's a queue, we put them at the end. Yeah? So now we have the two levels in the queue. And we just have to take out the next node out of the fringe, which is a C. And this is what happens. We get two nodes F, this should be an E, this F and G, and we add them to the fringe. So basically we now have all the nodes on one level in the fringe still, and this makes it the breadth first behavior that we always go level by level. And now we have to go on because we still have nodes in the fringe. So we go to D, we check whether D is a solution, it's not a solution. Okay, so that shouldn't have happened. No idea where this happened. Okay, so we check whether D is a solution, it's not a solution. So we have to check E, whether it's a solution, it's not a solution, if we don't have a solution in this. And then in order to check all of them, we just take them out and check whether they're going to stay for. Yeah? So the order in which we add the nodes to this list in this, or to this queue in this case, determines that we now do a breadth first search. Okay, so let's go to have another Mentimeter and now check how many nodes do we need to expand. If we have our breadth first Schnapsen light, my computer starts to behave strangely. This is the Menti, and here we go. Okay, so the question is differently, I'm sorry. The question is, if you have this card game that we had, we start with the ace, a 2, and a jack, a queen, an ace, and a king. At which level of the tree would you find the solution, and which nodes would you have to, no, at which level would you find the first solution? That's the question, sorry. Confused, yeah. And to be honest with you, I realize that the question is ambiguous because we have, you might start, do you start with 0, do we start with 1? So let's just stop here, show the results, because that might be the reason for the confusion. The idea is, in any case, that you explore the search level by level. So in the first expansion phase, you look at all the cards that are played. So you have a value of 11, 2, 3, 11, and 4. And then in the next level, you might get into playing the jack here and the queen here. And then on this level, still, when you play this card, so this is this level, you will get to the 22 value, because you go through all the options per level. Yeah? Sorry, that was a bit ambiguously formulated. Let's see what that means in terms of what we're doing here. Is that we try to understand how good or how bad are our algorithms in terms of time and space and so forth. So we have want to understand the performance of the algorithms with respect to the complexity of the problems. And again, the nice thing about having this generic approach is that we can look at the problems and the solutions very generically and try to understand the worst case complexity of the different approaches. So let's see what we can measure. We can measure whether we are complete. And that means that if there is a solution, do we find it with the approach that we have? The next thing that you want your algorithm to have is optimality. So does it always find the least cost solution? And in this case, we don't have costs yet. But if we, for example, want the fewest search steps, then do we have an algorithm that finds this or not? And then the most important ones is that we need measures for how long does it take us to get to an answer, and how much space and memory of our computers do we need. Because as we will see in a minute, this can become very problematic very easily. So in order to measure the time and the space, we have some general measures. And the first one is the branching factor that I already mentioned. And that is the number of options you have per state. So how many options do we have in the simple card game? We started with 5 cards. You had 5 choices. So the branching factor at that point was 5. And we write down here the number b for the maximum branching factor that you have in the tree. Usually you have also an average branching factor, but in order to determine the worst case complexity of this algorithm, we take the maximum. You also take the depth of the least cost solution, and then we have you also have the maximum depth of a search space. So there might be examples, particularly if you do not if you're not careful with duplications in your algorithm, that you might end up in circles, for example, and then your algorithm will just run forever. But if it doesn't run forever, then you can determine the longest search that you might have. For example, if we have the card game of 5 cards, where you play your cards, we know that the maximum depth is 5. If we don't fill up the cards, maximum depth is 5 because you can only play 5 cards. And that would be n in this case. So now let's evaluate breadth first search. So the question is, does it always find a solution if one exists? And the answer is, there comes the table. Yes, it does under one condition, and that condition is that the branching factor is finite. So if I have finitely many choices in my decisions that I can make, then breadth first search will always find a solution. That is not always the case. So if I would have a game where you can choose a rational number, then we would have infinitely many choices per decision making, or any rational number, any number, rational number, and the game would be infinite in the branching factor. But unless we have these sort of weird situations, in most of the cases, we have finite branching factors, so breadth search will always find a solution. Now comes the problem. The problem of the time complexity is that it is b to the power of d, or d plus 1, depends on where you start the counting, because in our tree, that we remember the A, B, C, D, E, F tree we had choices of 2, and it was 2 to the power of 2 to on the lowest level, so you have an exponential blow up. And this is exactly what we've seen before when we had the game with the fill up, where we went from the 5 times 4 times 2 to the 5 to the power of 5 when you filled up your cards again, because then you have 5 choices per level, and that means that you have an exponential blow up in terms of states that you have to look into. Now comes the even bigger problem, and that's why this is red. That's the space complexity, which basically means that I always need to have all of those, or a lot of things in the fringe. Namely, I needed to have the whole lowest level of nodes in the fringe. And this is, again, the number 2 to the power of 2. So this is, again, an exponential number of nodes that I need to have in memory. So the worst case complexity in terms of space for breadth first search is a b to the power of d, or b to the power of d plus 1, depending on where you start the count. It is optimal, again, when you have a finite branching factor. Okay, so how bad is this? And the answer is bad. So this is an example where you have a branching factor of 10. And that's not that much. Think about it. If you have chess, for example, you can already start, I think, with 8 pawns times 2, 16, plus the horses 4, I think, each. So you start out with 25 choices in chess. So the first move gives you a branching factor of 25. So that makes these 10 relatively small. Yeah. But even if you have this relatively small 10 branching factor of 10, and you go to a depth of 2, then you look already at about 100,000 nodes that you have to explore. In terms of time, our machines are, of course, nowadays very fast. And in some of the applications, you might have to wait for a couple of days, or let's not say a year, might be too much for a chess game, but for some real problems, this might be still feasible. But there is no machine that can have a petabyte of memory just to have our nodes in the memory. So the blow up in memory is something that makes this breadth first search approach impossible in practice. Because, I mean, we look at 10 examples here. So there's an alternative. And the alternative is exactly based on the same algorithm, but now instead of a FIFO, we apply a LIFO, which is the data structure of a stack. And a stack, I always like to draw like this. We now have the LIFO, and that is the last in gets the first out again. Yeah? It's like the pile of papers I have on my table. Always the top one is the one that I read, and not the bottom one. Yeah. So now we look at the same example. We start with A. We put it in our data structure. It's the only element. We take it out again, and we add the 2 children. And the 2 children are, as we've seen, B and C. And I put them in inverse alphabetical order. So then we get the agreement with the board. Okay. And then the first one that you put in, namely the B, you take out again. So we keep the C in here. So we had taken out the A, and we have now taken out the B. And we expand the B by adding its children. And the children of B are D and E. So we add them both to the stack on top, and we take out in the next iterative recursive step, we take out the top one, that's the D, and we expand it with the children of D, which are H and I. Now we have to expand H, there is no children. We have to expand I, there are no children. We have to expand E, there are 2 more children, which we have to add, and that is J and K. There's no space to add things now. So the top. We have k and I and j. We expand j, it's not a solution. We expand k, it's not a solution. We get the picture. We add h and f. And in that way, you go through the entire search tree. Now, just a different data structure, but the same algorithm. And it just depends on which one. So we take out the f, and I think I've forgotten to add all of those. So the order of exploration of this tree now becomes that you go this first, and then you do the backtracking until you have expanded and seen all the nodes. Yeah? So I leave out this because I guess it has the same problems in terms of ambiguity. But now the idea of the depth first search for our Schnapps and Lights would be that you just explore the cards from the left to the right. You would play them all, and then you would try another one on the way back. So you would go to, you would first play the ace, then you would play the queen, then you would play the jack, then the queen, then the king, and then you would find a solution which would be here you would play the ace. So we would find a solution here where we have more than 20 points. Of course, this is not the most clever way of getting to 20 points if you have to play 5 cards. But this is what depth first search would give you. Yeah? So let's evaluate the quality of the algorithm, depth first search now. Does it always find a solution if one exists? And unfortunately, the answer is no. Because in our algorithm, as generic as it is written down, what we don't do is any checking for repetition, for example. So it might be that we end up in exactly the same state again. So if you remember the jar thingy we had drawn, the state space for the jars, you fill the left-hand side with 5 liters. The next action is you empty the 5 liters again. You're back at 0, and if you're not careful, you're just filling it up again with 5 liters, and you're throwing it out again. And you can do that infinitely often. And depth first search would simply run into an infinite loop and die very quickly. So the pure version of depth first search, unless you do some very clever bookkeeping, is not giving you completeness. The time complexity, so the number of nodes that you have to visit in the worst case, is of course the same. Because remember, we had to go through all the nodes of this tree as well in order to find out that there is no solution, for example, in this case, or if the solution had been in the right-hand corner, we would have needed to expand all the nodes. So the time complexity is as bad. But the good news is that the space complexity only depends on the branching factor times the maximum depth until it finds a solution. Because you never keep the whole tree. You don't keep the full tree in memory. You only keep the parents of all the nodes that are so big in memory. Yeah, because we only expand the breadth of the tree when we need it. We only look at one branch at the same time. So if I go back to this image here, basically what you should be aware of is that you only have this branch in memory when we start. Let's put it like this here. So you only have this branch in memory plus these 3 nodes, nothing more. Then you can delete this H, and you only have, again, those in memory, or I think these 4. So there's always only a very small part of the tree that is in memory. And that makes depth first search far more economical in terms of memory space. Again, optimality doesn't hold because we don't have completeness in the first place. So here we are. So we have basically 2 algorithms. One where we know that it always gives us in almost any realistic case gives us an optimal solution, but we can't implement it because it takes too much memory. And the other one doesn't take that much memory, but it might not give us a solution. So that was for a long time was a big problem in AI. So in let's say the 70s and the 80s. And it took people really 20 years to come up with a solution. And I'm going to into that solution after this question.
Yeah, sorry. So you mentioned that for depth of search, we need to do keep power from the decent node. So is that the same for breadth of search? Because
no, you wouldn't run into an infinite loop because you have a finite branching factor. So you go to all the branches, and then on the next level you might run infinitely very long, but if there is a finite solution, you will always find it in this finite time.
Yeah, but this is a possibility that there are the same nodes in the range, and then it's bind from that nodes. Because if there's a loop, then the next range will contain the same nodes, and then we extend from that nodes. We also need to. We also.
Okay, so the question is whether you can also have this, or why you can't apparently have the same problem you have with depth first search, where you loop in your own in the fringe by having the same node twice in the fringe and always adding it to the fringe again. Why you can't have that in breadth first search and you can have it in depth first search? And the problem is that I'm not exactly sure whether that's the case, but I think because you add all the other options on the same level, you might reproduce parts of the same tree again, but you will also always consider the other options as well in breadth first search. So you always look at all the options. So if there is a finite solution, you will always find this finite solution, even though your fringe might be enormous and reproducing parts of it itself. Yeah. Okay, so let's get to the solution of the problem that you have one algorithm which gives us all the solutions, and one algorithm which doesn't, where the first one can't be calculated with the computer, and the second one it doesn't give us good results. And the solution is I think really nice, and it's based on understanding the complexity of these algorithms. So let's look at this. The first one is to say we can just do depth limited search, and we can do that in a depth first search way. So we keep the queue as our data structure, but then we say we only go to level 3. We only take the first 3 actions that we can take if we translate it into tree search. Yeah, and of course then we can just apply depth first search, and whenever we are at level 2, we do not consider the children of the nodes anymore. So basically what that says is we can now apply the queue data structure and have the good memory properties. But the question is, are we now finally complete? Can we find all the solutions? And the answer is, of course, no. Because if the solution is one step after my cutoff, then I will not find it, because I have this artificial cutoff. So we have an algorithm that is depth limited search, solves the infinite path problem, because we will never end up in these loops, because after n steps we stop. But if the solution is after my L steps, then the algorithm is not optimal. So it doesn't buy us that much. The time complexity is, of course, up to the length, so we have to expand the full tree. And the space complexity is smaller up to the length. We only have to have those that are relevant in memory. Yeah, you have a question?
To prevent from getting into a loop, all you need to do is keep in memory your path until then, right?
I have to think about this, because I was doubting as well. I think the solution for addressing the depth first search problem is more complicated, because if you want to check for loops, you again have to have the full tree in memory. So you can't throw away the the nodes that you haven't visited. And the trick of the space complexity is that you can throw away all the things that you've seen before. And if you have this duplication check, you need to keep the nodes.
Not the entire tree, just the part you follow.
No, but your loop could be at some other place of the path. So let's take it offline, or I have to think about it more carefully. But this is what the literature says, is that you can't do that way. And I trust it. So, but this is a nice way for doing things, because we have now the depth limited search, and the solution is simply to iterate this depth first search until you find the solution. So that's why it's called depth first iterative deepening, because we start with a depth first search of 0. If we find the solution, fine. If we don't find it, we continue with depth first on level 1. So the trick is now, let's look at this example, that if we have if we start with limit 0, we just look at the root of the tree, and we check whether it's a solution. Yeah. If it's not a solution, what do? We increase by 1 level, and now do depth first iterative depth first search up to the level 1. Yeah. So now we take part of our pretty big tree, possibly, but only expand it to level 0. And we do depth first search, so that's important. We don't do breadth first search, even though it looks, in this case, it still looks like depth first search. So we take the first node, we check it out. It's not a solution. We do this side. It has no children up to this level because we restrict the level, the depth. And then we go on and expand all the nodes in the depth first way. Okay, we don't find a solution, so we throw everything out again. We start from scratch, but now we do depth first search to level 2. Yeah? How do we do that? We start from the top node. We ignore that we have already done it. We ignore everything we knew before. We do a depth first search, so we go to the left node, we go to the depth, we backtrack because after level 2 we haven't found a solution yet. So we do the backtracking, and then we go down until we've seen all of them in depth first search way. Yeah? At each level we only have the b times m maximally in memory, so the memory is always small. And we do it again. If we haven't found the solution for level 3, we throw everything away and we start again from scratch. So basically now it's limit 3, and we do back depth first search, which gets us down to this node. We do the backtracking, and then we go step by step from the left-hand side until we've expanded with depth first search up to level 3 everything. So completeness is yes, because you can never end up in the infinite path. And if there is a solution on a length L, depth first iterative search will always find it. Now, I have a Mentimeter again, but we can also do it by show of hand in the interest of time. Oh no, let's do it with this one. And the question is, this method where you throw away so much, isn't it so stupid? So how many nodes more than you would necessarily have if you have, for example, depth first search, how many more nodes do you have to investigate if you always throw away everything you've done up to now and do it again? So do you think this is 1.2 extra work? Is it 12 times extra work, or is it 120 times extra work if we go to the asymptotic, namely lots of depth? So this doesn't hold in small depth, but on the longer depth. So for example, 10, if you have a depth of 10. So do you think it is a factor of 2%, 1.2, or a factor of 12, or a factor of 120? Remember that we redo everything at every level. We redo everything. In other words, how stupidly inefficient is it to do this approach by removing everything just to get completeness? Okay. And this is, I think, why my question was quite suggestive, but still, most of you got it wrong. And this is probably why it took people so long to really see why this is really an interesting and good algorithm, because the answer is really 1.2. So the factor that this makes life harder for the algorithm is very, very small. And let's see why this is the case. If my algorithm still does it. So why is this the case? So in principle, what you do is when you go from one level to the next one, suppose we found a solution at level depth, D, then what we've done is that we've done the last level where we have the b to the power of d number of leaves that we have to check. We've done that only once, that is when we found the solution. The level above, where we have to expand on the depth 1 up, d minus 1, we have to do twice, because once we do it for real when we find the solution, and one when we had the iteration before. Yeah. So basically, for each level, you just add up all those numbers, and you get to this sum, which gives you the extra work. And then there is some mathematical magic that you can apply here, some asymptotic analysis, and basically what you get out with is a factor in the order of b minus 1, so the breadth minus 1 divided by the breadth, times the complexity that you have if you apply depth first search. So that means that if you go to relatively high numbers, like 10, depth of 10, then your factor is really only 0.2 more than you would have normally. So if you look at this for a depth of 5 with a branching factor of 10, then basically you have to redo. You're only looking at this amount of steps. So you would have to do the 100,000 anyway, and only 23,000 are the ones that come extra. Yeah? So that is surprisingly little extra work. And why is that the case? The case is always that if you have a high branching factor, let's say 4 here, and you come to the next level, then the number of leaves that you have to check on the leaf level is always so much higher than the number of the leaves, the nodes before, that they are that it doesn't really matter to redo them that often. And in these small numbers, the factor is relatively big still, because we have this 1 before, so we have to do 16 plus 5, so we have 21 nodes here. But already in the next level, we're looking at 80 something, 80s, 72, and then the numbers that are above are so comparatively so small that mathematically and also in runtime, in real runtime, it doesn't really make a difference. So I think this is a really nice example for a very smart algorithm that's very simple and even from the outside quite dumb looking. And it was found by these very generic methods, looking at the structure of these search trees that you build for generic problem solving. And this is something that really is now widely usable for many, many problems. So if we sum up the properties of the algorithms, this is then what really matters for us. It's if you have a breadth first, as I said, the big problem is the space. Depth first, the big problem is the completeness. And the iterative deepening algorithm is now the solution basically to both of these problems and combines the good properties of both by just increasing the time complexity in a constant, in a linear way. So in terms of complexity analysis, this can be ignored. So the worst case complexity is really simply exponential in the same order of magnitude as you would have with depth first search. That's good news. Okay. So I still have 5 minutes, which I want to spend on the direction of search. So we have now started with the decision of I have 5 cards and I want to play them, and my action is to play a card. But I could have represented the same problem in a different way. I could have said, okay, my states in which I start are cards have been played, numbers are done, and I take cards back. So it's a very weird way of thinking. Nobody would do that, but it would be a valid way of representing the same problem. Or in the jar example, you just start with the example of a jar that has 1 liter, and you try to go back, how can I do this so that I get to 0, 0. So that matters because in some of the problems, one direction might be more efficient than another. So look at this maze example where we have an initial state, C3, that's the one in the middle, that's me, and now I can move towards the goal, and then I have to explore these paths. So this one would be the end of this is the end of a walk in one direction until I have to make a decision. It's another variation. The one choice would be going down there. One choice would be going up here. Then I could go to the left. Then with this one, I could go down. And then I have 2 choices. So it's an abbreviation for the state space of going through the maze. And of course, I could also say, I start with the place where I want to be, and I look for the places where I have to go and be before reaching my goal. And in this case, this would be starting here. I have a choice here, and basically, I would also get to a solution. Yeah. In this case, it doesn't really make a difference. This tree is a bit smaller, so I have fewer nodes to visit. But there are cases where there is a big difference in the branching factor between the 2 directions. Yeah? So you all know mathematics, I guess. Most of you know. Maybe some people don't. So the big question we all wonder about, of course, is whether Matti is a descendant of Willem von Oranje. Yeah? So what we have is records of who are the parents of Matti, and we also have all the children of Willem von Oranje. And so we just need to go through all the records until we find either from Willem von Oranje that Matti is a descendant, or we start from Matti and we decide whether one of his ancestors is Willem von Oranje. Which way would you look? Because you understand that this is, again, it's a simple search process. We have a state where that's Matti, and then we have the state where we know you are the parents, and the question whether it's a predecessor or not. Which direction would you search? Yeah. You would start from Willem von Oranje. There is someone next to you.
Probably actually start from Matti because Matti has only 2 parents, while Willem might have like 5 children.
Exactly. So if I start with all the children of Willem von Oranje, I think historically it has been shown that there are the average is 3 children. So you have a branching factor of 3 in your tree. So we would have the distance, of course, is the same because whether Willem is an ancestor is as long as Matti a descendant, so it's the same distance. But the branching factor so matters now. And indeed, the branching factor in the way when we start with Willem von Oranje, it's always 3 or 4 children, or sometimes 2, but on average it's 3. And if you go from Matti and via the parents, it's always 2, because we all have 2 parents. Yeah. So starting from Matti, you have a branching factor of 2, and starting from Willem, you have a branching factor of 3. Yeah. So it makes a lot of sense to start with. So this is what's called data-driven. When you start from Willem von Oranje, then you have to look, if n is the distance between Matti and Willem, then you have to look through 3 to the power of n different records to find whether they are related or not. Yeah. Yes, that also exists, but then you need to find each other, and that's quite difficult to coordinate. And of course, then the other thing we have seen is that if you start from Matti, then you only have to search for 2 to the power of n. And if you say this doesn't make a difference, think again, because 2 to the power of 10 is, if you think there are 10 generations between Matti and Willem, then you have 1,000 records that you have to look into, or almost 60,000 records that you have to look into. So it's 60 times as much work to do this in the direction from Willem as opposed to the direction from Matti. Okay, so we're almost done, and in time, that's good. So to summarize, the idea is really that we have these generic problems, and the search algorithms that we've seen today give us the generic solutions to these problems. We have looked at search algorithms, properties of those algorithms, very important, the directions, and we will look into that, not today, but on Friday. Practice Schnapsen, keep up the good work, and start looking into the theoretical and practical material. And thanks a lot, and see you on Thursday.